So here are the topics that we're going to be covering today. We're going to be covering
we will be covering light and energy, hydrogen emission, and reviewing molarity, dilution, and titration. Light and energy. So in class, you know about how light behaves, right? There's different sources of light, like infrared, microwave, X-rays, and gamma rays, just to name a few. But light has two specific behavior patterns. One of that is wavelength, and the other one is frequency. So you know that in class you learned about lambda, right? So lambda is, well, the wavelength. And then frequency is that little weird shaped V thing that would, that's frequency. So when you have a higher frequency, you'll have a shorter wavelength, like in the first, like the above picture. And then if you have a longer wavelength, you have a lower frequency, which is the one on the bottom. So here's the equation for frequency, and that would be c, which is the speed of light, is equal to the lambda, which is the wavelength in meters, and the frequency, which is in 1/seconds. So speed of light is always be meters per second. So and it's a constant. So speed of light doesn't change. But lambda and wavelength, lambda and frequency, they will both multiply together to become the speed of light.
Alrighty, so let's try a practice problem. I know in lecture, Dr. E didn't really have time to go over any with y'all. She kind of just introduced all the equations, and then on Monday, I believe, she will do like a whole bunch of practice problems. So for now, let's go ahead and get like a really quick head start. Try this practice problem. A red laser beam has a wavelength of 751 nanometers. What is the frequency of the laser? So how do we solve this problem? First, you're going to need to know the equation to solve the problem. And for the equation, well, there's only one equation that relates frequency and wavelength, which is this one, right? We have frequency, wavelength, and c, which is the constant of the speed of light. This is really important. Make sure you know what each symbol represents, and make sure you know their units. So since the equation has wavelength in meters, we cannot just plug in 751 nanometers into the equation to solve for frequency. We need to first convert nanometers to meters, and this is a conversion that you have to memorize, by the way. So you might as well like get used to it now. We're gonna put meters on the top and nanometers on the bottom to cancel out our units. 1 meter is equal to 10 to the 9 nanometers. And if you do the math, you should get 7.51 times 10 to the -7 meters. Okay. So now our units match the required units for the equation. So all the units will cancel out nicely, and they'll left over with our frequency, which is in 1/s. So when you plug in the math, we're going to divide by the other side. So frequency should be equal to 4.00 times 10 to the 14, 1/s. Okay? All right.
So how light behaves, and so light behaves like a particle, which is another name for a photon. So what photons do, they quantize energy levels of energy. So remember in class when Dr. Esfandiari was talking about stairs, and like there's like what you call it, like the staggered stairs, like you know when you go up to like when you go up the stairs in your house or your dorm or your apartment, and you have to go up those stairs. It takes energy for you to get from the next level up. Unlike a slope, which is like you can take as little energy as possible to like work your way up. But in a stair, it has to be, you actually have to put in energy. Same thing with photons. Photons need a specific amount of energy for them to jump up the stair. So quantized energy is energy that is a set amount. So an example, you're at a grocery store buying photons, and you can buy them for $3.50 or $4. You cannot go to the register and ask to buy a photon for $3.88 because the store system doesn't register that price. So it's either $3.50 or $4, nothing in between. So that whole getting over that hump sort of a deal. So here's the energy equation. So E is equal to the H times the frequency. Frequency, you already know what that is. E is always energy in the units of joules. And H is a constant named after Planck, which is named after Planck, so it's Planck's constant. So that number will always stay the same, which is 6.63 times 10 to the negative 34 joules per second. So,
okay, so let's try another practice problem. What is the energy associated with a green laser beam that has a wavelength of 525 nanometers? So this one, you need to write down the equation that you need to solve first. So far, there's only one equation that we can use to solve for energy and frequency, which is the one we just looked at. So it's going to be this one right here. E equals frequency times the Planck's constant, which Esfandiari will give you on an exam. For this one, we just plug in the okay, oops, there's a mistake. This like should be, hold up. Yeah, this is not wavelength. So the question is, I changed it to make it easier for y'all.
Just feel like recording on my laptop. I don't know why. Sorry everyone, I'm losing my mind.
So the problem is, what is the energy associated with a green laser beam that has a frequency of 5.71 times 10 to the 14, 1 over S? And then, like I said, there's only one equation that relates energy with frequency, and that's going to be this one right here. Energy is equal to Planck's constant times frequency. So this one is really simple. We just plug in the variables and solve, but make sure you pay attention to units. So energy will always be measured in joules, and Planck's constant will always be in joules per seconds. Wait, is that right?
Yeah, joules per second. And now Planck's constant is the J over the S. So yeah, that's right. Oh, wait.
Wait, is that right?
Oh, wait.
It's only joules, right? No.
No, it should be joules per second. Wait, what's frequency again? Come on, time out, everyone. Technical difficulties. The brains are not working.
Okay, so it's joules times seconds.
Oh, joules times seconds.
Yeah, that makes sense because the S needs to cancel out. Okay.
Oh.
Dang it. Okay, I'm so sorry. There's another mistake. Basically, yeah, so Planck's constant will be measured in joules times seconds, which makes sense because frequency is multiplied by 1 over S.
Oh, joules.
So the seconds on the top will cancel out with the seconds on the bottom, leaving you with only joules on top.
Yeah, because joules over seconds is actually watts.
Okay, nice. Okay, so sorry about that. So let's move on. Here's another practice problem. Which wave has a higher energy and how do you know?
Well, let's see here. Since energy has to deal with frequency, right? So if we have a higher frequency, that means we have more energy. So, and if we have a higher frequency, that means it's a very shorter wavelength because it goes like there's more vibrations. So A would be the one that has the higher energy because it would have the higher frequency, but the shortest wavelength.
Yes, so basically, to solve this problem, you don't even need to look at the equation. You can just think about the electromagnetic spectrum. If we think about gamma rays and X-rays, they fall right here on the spectrum, and look at their frequency. It's very, very, very high because we have many, many waves in a certain amount of distance versus radio waves, which are very, very large. So they have a much lower frequency because there are fewer waves for like 1 inch versus gamma rays and X-rays, which have many, many waves over like 1 inch, for example. This also makes sense because if you think about gamma rays and X-rays, they're very dangerous. You need to wear like very protective gear in order to be around gamma rays and X-rays. And this is because they have a high frequency and a very high energy. And that energy can be very damaging. So that's like a really good way to connect real life evidence to like the equations that you're learning, so that you can get like a better idea of how they work. Okay.
The other equation you learned in class was Rydberg's, right? So Rydberg's energy is Rydberg's constant is 2.18 times 10 to the negative 18 joules. So this constant can actually help you out learning about emission, which is how much energy is being emitted or absorbed. So this specific constant deals with hydrogen. So hydrogen is, well, just one proton that can go up and down in different energy levels. So back to that whole example of you climbing up a staircase, hydrogen is the one that can do it. Hydrogen is the one that does the whole emission thing. So the equation for emission is E is equal to the negative RH times the 1 over n final squared minus the 1 over initial squared. So n final would be the point in which hydrogen will land based on the level, and then n initial is where it started. So kind of like what you will call it, what do you think? It's like jumping up back and forth. Like you jump up then bounce back, something like that, with energy levels.
Yes.
Yeah, so it jumps up and and how much energy it takes for hydrogen to jump up, and then how much energy it takes for it to jump back down, in a sense. So, oh, and also note that if energy is negative, that means it's releasing energy, and if energy is positive, that means energy is being gained or absorbed. So, this is sorry. Okay. So here's a question. Here's a question. So find the wavelength of the electromagnetic radiation that is emitted from an electron relaxes. Oh, electron relaxes from 9 is equal to 3 to n is equal to 1. So, oh wait, did I do this wrong? No, sorry, I didn't do it wrong. Okay, so it's the energy that's being emitted from an electron. So it's releasing energy. So that means it's going from energy state of 3 to energy state of 1. So here's your equation. We know that n final is equal to 1 and n initial is equal to 3. So we know that 1 squared is 1 and 3 squared is 2. Wait, 3 squared is 2. 3 squared is 9, sorry. And we plug that into our equation. And we end up getting E is equal to 1.94 times 10 to the negative 18 joules. Now then, since it says emitted, what would be the sign of energy?
So when an electron emits energy, the sign on energy must be negative, because in order to move because when energy is emitted, that means the electron is moving from a high energy level, which is n equals 3, to a lower energy level, which is n equals 1. And in order to do that, you need to remove some energy from the electron, because you're making it go to a lower state. So when something is losing energy, we put a negative sign to represent that this is a loss of energy happening. And then, so this should be a negative sign right here.
Yeah, it will be a negative sign.
Okay, yeah, there we go. And then likewise, if an electron is moving from like n equals 1 energy level to up to like n equals 4 energy level, because we need to add energy to the electron to make it move up a higher step, the sign on energy must be positive, because we are giving the electron energy. We're adding something into the system.
Molarity. So everyone knows that, well, molarity is, well, moles over liters. So why don't we do a little quick problem right here? So what is the molarity of 25.00 grams of potassium hydroxide in a 200.0 milliliter volumetric flask filled twice to the top with water? So how would we set this up? Well, we would, my chat box is gone. That's awkward. Sure. So first we would set it up by converting the grams into moles, because we know that molarity is, well, moles over liters, so we might as well make them into moles. Makes life easy. So we take 25.0 grams, multiply by 1 mole of KOH divided by 56.1 grams of KOH, and we end up getting 0.4456 moles of potassium hydroxide, right? Now then, we take that hydroxide and we divide it by the volume. Why is it 0.200 instead of 200? Out of curiosity.
Because you want to make sure that units match the equation given, which is always very important. Units will never go away. Molarity is always measured in moles per liter. In the problem, we're given grams of KOH and milliliters of solution. So we cannot just plug these numbers into the equation to divide and get our molarity, because the units won't cancel out and they won't match the proper units for molarity. So we converted grams to moles using the molar weight, and then convert ml to liters by dividing by 1,000. And then now you can use these numbers, plug them into the equation, and then solve for your molarity, which is 2.23 molars.
Mm-hmm.
Alrighty. Next is dilution. Dilution, the formula is going to be M1V1 equals M2V2. So here we have a volumetric flask filled with 250 ml of 0.690 molars HCl. And if you want to make the concentration become 0.23 molars, with a final volume of 300 ml, how much water do you need to add? So this problem is definitely a dilution problem, right? Because initially we are given 0.69 molars HCl, but we want 0.23 molars HCl. So this is a really good indicator that this is a dilution problem, and you have to use this equation M1V1 equals M2V2, because we're making the concentration of HCl go lower to 0.23. So let's try it. We're gonna plug in our variables. M1, which is our initial molarity, is gonna be 0.69. M2 is gonna be 0.63, because that's what our final molarity will be. That's the one we want. We don't know what the initial volume will be, but we do know that we want a final volume, the problem literally says it, to be 300 ml. So we need to add some amount of water to dilute this very, very concentrated solution of HCl.
So using M1V1 is equal to M2V2, we plug in all of our numbers in. M1 is 0.69 molar. V1 we don't know, because we don't know what V1 is. 0.23 is the concentration we want, and then 200, dang it, it's supposed to be 300. That was it. This 250 is supposed to be 300 0.00 milliliters. My apologies. That's 69. That's 300. There we go. Apologies. Present. Apologies. So 300 is the final volume we want. Wait, where is this recording? 300 is what we want. So V1 is equal to 0.23 millimolar times 300 milliliters divided by 0.69. Now then, this V1 is the volume required of the acid needed, not the volume of the water. So how will we find the volume of the water?
Wait, I'm kind of confused, because you said the volumetric flask already has 250 ml?
No, that's the volume. No, so the acid itself is in 200. So the amount of acid that you have is 250 milliliters, right? But that's not the initial volume you need. The initial volume for the dilution that you will need is after you take it from this stock solution.
Oh my God, you should have
I should have
specified that.
stock.
Because we're assuming that we're gonna add this water into this flask already.
Oh, stock.
So you should just say, I'm gonna change this.
A stock.
This is super confusing.
I am so bad with words. My apologies, everyone. Ah, dang it. I knew I should have read this before I came here.
Yeah, so I'm really confused because so we're not adding, so 250 ml is not in our flask, right?
It's not in our flask. It's a different whole little flask itself. It's its own flask. So we are taking acid from that flask into a different
So I'm gonna just
volumetric
say, I'm gonna just erase this. You have on stock.
Oh, okay.
Because that's like very misleading, I feel. It's like
I
the
don't
wording
know.
is very confusing.
I don't know how they would probably do that Shaniqua stuff, but
They do?
they did. When I did it, they gave me those weird problems like that just to throw you off. The times have changed. All right, moving on. So V1 is the 100 milliliter required acid that you need to make your stuff, to make your molarity. But that's not how much water you need. The amount of water is actually 200 milliliters. So basically, it's the final volume is equal to the amount of acid and plus the amount of water. So the amount of water is just the final volume minus the amount of acid. So
Wait, this didn't change.
no, because they were all duplicated of each other. And
Yeah.
Sorry, slight miscalculations on my part. So you need 200 milliliters of water, 200 milliliters of water. You will probably have to do this in the titration experiment. The titration experiment where you have a stock solution and then you have to do the math in order to find how much water you need to get your required concentration. So.
Okay. So next is a review of titration. If you remember, titration is a technique to figure out how much acid or base there is. I believe that's the experiment you are all doing in lab this week. Either this week or next week, I'm not sure. But basically, titration is to figure out how much acid or base there is. And then endpoint is when you've added the amount of moles of base required to neutralize the moles of acid. So let's try a practice problem. This problem is really similar to one from one of my old lab exams for Chem 1A. Even though they don't pass back these lab exams to us, I remember this problem because it was very difficult. So that's the one we're doing today. A vitamin X pill was crushed up and titrated to endpoint with 14.5 ml of 0.467 molar sodium hydroxide. How many grams of vitamin X was in the pill? And then the molar weight of vitamin X is 42 grams per mole. And a hint is vitamin X is a triprotic acid. So let's figure out the steps to this problem because this is a very complicated, big problem. The first hint to look at is the pill was titrated to endpoint. So I recommend you ask yourself, what does endpoint mean again?
Endpoint means where all of the hydrogen, the H pluses, are all neutralized by base.
Exactly. So endpoint means a certain amount of moles of NaOH will be added to neutralize the moles of acid. So to start, we should figure out how many moles of NaOH were added to the flask. Because if you drew a picture of this, our flask will have the vitamin X in it, and inside our burette, which is like that long pointy dropper, we're gonna turn it, and then it's gonna drip down some NaOH into the flask. So since we know the volume of NaOH and the molarity of NaOH, we can just plug this into our equation for molarity and solve for moles of NaOH. Remember to convert the mLs into liters. Otherwise, your answer is going to be off by 1,000. So if you do the math, you should get 6.7715 times 10 to the negative 3 moles of NaOH. Okay, so now we have moles of NaOH, but we don't know moles of acid yet, because if we did know the moles of acid, we can convert it to grams using the molecular weight. However, the hint here is that one OH ion will neutralize one H plus ion. So since vitamin X is a triprotic acid, how many hydrogen ions will be in one molecule of acid?
If it's like mono meaning one, di meaning two, I would assume tri would mean three, right? So it's three acids. It's three acids in your vitamin X.
Three
Like
H ions.
H plus ions, sorry.
Yes, exactly. So the prefix should give you a hint that there's going to be, the formula will look something like H3 something something something. Because we're not given the formula, this is a really good hint to go off of to determine how many moles of NaOH you'll need to neutralize the moles of acid. Because the OH will not react with the other part of the acid. It's only going to attack the H plus ion to try and neutralize it and form H2O, which is water. So given that hint, let's convert moles of NaOH to moles of the acid. Here I have moles of NaOH, and then because one NaOH ion or one NaOH molecule has one OH ion, I'm going to need 3 moles of NaOH to cancel out 1 mole of vitamin X. Because I wrote like a pretend formula right here, H3X, 3 OHs will neutralize the 3 hydrogens. So don't be surprised if your moles of vitamin X will be a much smaller number than the moles of NaOH, because this acid is very, very strong, quote unquote. So you're going to need greater amounts of base to neutralize it versus like a classic acid, like a classic monoprotic acid, like HCl, where it's really easy. You don't need to convert anything. The moles of NaOH would just equal the moles of acid. Here we have to do like an extra step to figure out how many moles of NaOH we need. So now we have moles of vitamin X acid. The problem gave you the molecular weight. So cancel out moles of vitamin X, and you're going to be left with grams of vitamin X, which is 0.095 grams. This is going to be really similar to the lab that you guys are going to be doing for titration. So if you need like a refresher problem, you can always refer back to this PowerPoint to help you out. Okay? So thanks for joining us. We will see you all in lecture.